Max Planck's role in shaping modern physics can be understood as one of the most profound transformations in scientific thought, comparable to the revolutions brought by figures like Isaac Newton and Albert Einstein. Before Planck, physics was built upon classical principles that described the behavior of matter and energy in a continuous, predictable manner. For centuries, scientists believed that nature followed smooth, uninterrupted patterns, and this belief guided the understanding of heat, motion, light, and all physical forces. Planck's contribution shattered that world view and replaced it with a vision of nature based on discrete units, uncertainty, and fundamentally probabilistic behavior. His work became the origin of quantum theory, which today forms the basis of modern physics and underlies nearly all advanced technology. Max Planck entered the scientific world at a time when classical physics seemed almost complete. The laws of mechanics and gravity developed by Newton, the equations of electricity and magnetism formulated by Maxwell, and the principles of thermodynamics were all considered final achievements. Many scientists believed that there was little remaining to discover. In fact, a well-known physicist of that era, Lord Kelvin, famously suggested that physics was essentially finished, with only a few minor details left to refine. Planck, however, was not convinced by this sense of closure. His early studies in thermodynamics already demonstrated that the behavior of heat and energy contained unresolved contradictions. The specific problem that brought Planck to the forefront of scientific innovation was the question of blackbody radiation. A blackbody is an idealized physical object that absorbs all radiation falling onto it and emits radiation based on its temperature. Scientists had tried to calculate the precise spectrum of light emitted by blackbodies and had failed. Classical physics predicted that as the wavelength of emitted light became shorter, the intensity should increase indefinitely, leading to what became known as the ultraviolet catastrophe. However, experimental measurements showed that intensity reached a peak and then declined. No classical equation could explain this behavior, and the discrepancy represented a major crisis. Planck approached this issue with a combination of mathematical skill and philosophical caution. He did not set out to overthrow classical physics. In fact, he deeply respected the traditional framework and initially believed that his solution would reinforce classical thermodynamics. Yet, through a sequence of logical steps, he arrived at a conclusion that contradicted the foundational assumptions of continuous energy. He found that he could correctly describe blackbody radiation only by assuming that energy was emitted not in a smooth flow, but in discrete packets, which he called quanta. This idea was radically new and deeply unsettling, even to Planck himself. Energy had always been viewed as infinitely divisible, but Planck's equation required it to come in fixed units that depended on frequency. The introduction of the quantum was not just a mathematical trick. It implied that the workings of nature were fundamentally discontinuous. At extremely small scales, the world could no longer be described using classical laws. Light and heat could not be fully understood using waves alone. They exhibited particle-like properties that defied classical explanation. Planck's constant, a numerical value that determined the size of each quantum, became a central pillar of all future quantum theory. This constant appears today in every branch of the field, from atomic physics to quantum computing. Planck himself did not immediately embrace the full philosophical implications of his discovery. He saw the quantum as a necessary means to solve the blackbody problem, but hoped that classical physics might eventually be restored in a more complete form. However, other scientists recognized the deeper significance of Planck's result. Albert Einstein, in particular, applied the quantum concept to the photoelectric effect, where light causes electrons to be ejected from metal. Einstein argued that light was composed of particles, later called photons, each carrying a quantum of energy. This further disrupted classical views and initiated the development of quantum mechanics. Planck's role in shaping modern physics, therefore, was not limited to a single discovery, but extended to influencing the entire direction of scientific thought. His work opened a new field of inquiry and provided the tools that others would use to explore atomic and subatomic behavior. Scientists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built full theoretical frameworks using Planck's initial insight. These theories described electrons orbiting nuclei, energy levels in atoms, wave, particle duality, and the uncertainty principle. Each breakthrough reshaped humanity's understanding of reality, and each owed its origin to the concept of the quantum that Planck introduced. Beyond the scientific consequences, Planck's work altered the philosophical interpretation of nature itself. Classical physics assumed determinism. Given enough information, one could predict future outcomes with complete precision. Quantum theory revealed that at the smallest scales, outcomes are probabilistic rather than deterministic. Reality, at its core, involves uncertainty. This shift challenged long-standing assumptions about knowledge, causality, and the nature of existence. Planck himself maintained a conservative philosophical stance and did not embrace all the speculative interpretations that arose from quantum theory, but his discovery nonetheless forced the scientific world to reconsider the meaning of physical laws. Planck's impact also extended into education and scientific leadership. As a professor in Berlin, he mentored many leading physicists and actively supported scientific dialogue. His lectures helped develop the next generation of researchers who would carry quantum theory forward. He played a major role in forming scientific institutions and guiding research during times of political upheaval. Even during the difficult years of World War I and later under the Nazi regime, Planck argued for the independence of science from ideology. His personal integrity became an example of commitment to knowledge in the face of social pressure. The influence of Planck's quantum theory reaches into everyday life through technology. Modern electronics, digital communication, lasers, medical imaging, nuclear energy, and semiconductor devices all rely on principles that originate from quantum mechanics. The ability to understand and manipulate atoms and electrons depends directly on the conceptual framework that began with Planck's equation. Without the quantum, smartphones, computers, satellite GPS systems, and much of modern medicine would not exist. Planck's discovery not only changed abstract theory, but also reshaped human civilization's technological capabilities. Thus, Max Planck's role in shaping modern physics can be summarized as the catalyst of a scientific revolution that replaced certainty with probability, continuity with discreteness, and classical predictability with quantum complexity. He challenged the most fundamental assumptions of physics and opened the door to new theories that continue to expand human understanding. His influence spans the scientific, philosophical, educational, and technological domains of modern life. Even if Planck himself was cautious about fully embracing the consequences of his work, history has recognized him as the originator of a new world that defines physics today. His legacy endures not only in equations and textbooks, but in the very structure of the scientific questions humanity now asks about the universe. Planck's role in shaping modern physics becomes even clearer when examining how his discovery gradually transformed scientific thinking across decades. At the time he introduced the quantum concept, he did so reluctantly and viewed it as a temporary mathematical construction. Yet, the scientific community soon realized that it was not simply a clever adjustment, but a fundamental description of how nature behaves. This realization did not happen overnight. Many physicists were hesitant to abandon classical physics, as it had been extraordinarily successful in describing the motion of planets, the behavior of mechanical systems, and the propagation of electromagnetic waves. The idea that nature might operate in discrete jumps rather than smooth flows felt unnatural to many. Planck's contribution, therefore, was not just scientific, but also intellectual and cultural. He forced the scientific world to consider that its deepest assumptions could be incomplete. The shift was gradual, but the evidence built steadily. As experiments became more precise, classical theories repeatedly failed to explain the results. The behavior of electrons in atoms, the stability of atomic structures, the emission and absorption of light at specific frequencies, and the interactions of small particles could not be reconciled with classical physics. At first, these mismatches appeared as isolated puzzles. Only when seen through the lens of Planck's quantum concept did they form a coherent pattern. His constant appeared everywhere, steadily proving itself indispensable. This consistency strengthened the idea that the quantum was not a temporary invention, but a natural law of the universe. Planck's influence on Einstein was one of the most important turning points. When Einstein applied the quantum concept to explain the photoelectric effect, he provided clear experimental justification for the particle nature of light. This marked a dramatic shift in physics. Light had long been understood as a wave, and Maxwell's equations supported that understanding. Einstein's interpretation suggested that light also behaved like a stream of particles, later called photons. This dual nature of light became a cornerstone of quantum mechanics. While Planck initially hesitated to accept Einstein's interpretation fully, he recognized the importance of the work and publicly supported Einstein even when other scientists were skeptical. Their intellectual relationship demonstrated Planck's openness to ideas that extended beyond his own assumptions. Over time, quantum theory evolved into a complete framework describing atomic and subatomic behavior. Niels Bohr developed a model of the atom that relied on Planck's quantized energy levels. In Bohr's model, electrons could only exist in specific orbits around the nucleus, and they emitted or absorbed energy only when jumping between these levels. This explained atomic spectra, something classical physics could not do. Werner Heisenberg and Erwin Schrödinger later developed different formulations of quantum mechanics. Heisenberg created matrix mechanics, focused on observable quantities, while Schrödinger developed wave mechanics, based on differential equations. Both approaches ultimately described the same reality. Paul Dirac unified quantum mechanics with special relativity, leading to predictions that were later experimentally verified. Throughout this development, Planck's constant remained central. Every theory, every formula, and every experimental measurement in quantum physics relied on it. Its presence in all quantum equations served as a constant reminder of where the revolution began. Although Planck did not personally build the full machinery of quantum mechanics, the structure could not exist without his foundational discovery. His role was similar to that of a seed that grows into a vast tree. Even if he did not determine the shape of every branch, the existence of the tree depended on the seed. Planck's impact was also shaped by the historical context of his life. He lived in a period when Germany was undergoing major political and social changes. As a respected scientist, and later as the president of the Kaiser Wilhelm Society, now the Max Planck Society, he found himself in positions of responsibility during difficult times. He believed strongly in the international nature of science and in the idea that scientific progress should be independent of nationalism or political ideology. During the First World War, he attempted to maintain scientific cooperation, though his efforts were often constrained by broader political forces. The rise of the Nazi regime presented even greater challenges. Many scientists were targeted due to their ancestry or beliefs, and academic freedom was severely restricted. Planck spoke up for several persecuted scientists, including Einstein, and worked privately to defend them, though his influence had limits. Additionally, Planck suffered intense personal tragedy during this period. His eldest son died in World War I, and during World War II, another son was executed for being associated with an attempt to resist Hitler's dictatorship. These losses deeply affected him, yet he continued to advocate for the preservation of scientific integrity and rational inquiry. Despite hardship, Planck's commitment to science was unwavering. After the Second World War, he helped rebuild scientific research in Germany. The society renamed in his honor, the Max Planck Society became a leading institution in global scientific research, supporting discoveries across physics, chemistry, biology, and more. This institutional legacy reflects not just his scientific achievements, but also his belief in the importance of scientific collaboration and the pursuit of knowledge. Understanding Planck's role in shaping modern physics also requires examining how quantum theory changed not only scientific models, but also philosophical perspectives. Classical physics was based on predictability and certainty. If all factors were known, one could in principle calculate the past and future states of any system. Quantum theory replaced this determinism with probability. At the atomic scale, one cannot predict exact outcomes, but only likelihoods. Heisenberg's uncertainty principle, for example, states that certain pairs of variables, such as position and momentum, cannot both be known simultaneously with complete precision. This was not due to limitations of measurement, but a fundamental property of nature. Such ideas challenged deeply rooted assumptions about reality and human understanding. Planck himself was cautious about the more radical philosophical interpretations of quantum mechanics. He believed in the existence of natural laws and did not welcome interpretations that seemed to replace law with randomness. He accepted the quantum as a mathematical and physical necessity, but did not fully embrace the more abstract discussions about what it implied about the nature of reality. This cautious stance highlights Planck's conservative scientific personality. He respected tradition and viewed science as a gradual refinement of understanding rather than a sudden and sweeping replacement of ideas. Yet, ironically, his own discovery forced such a sweeping change. In the decades since Planck's time, quantum theory has expanded into fields he could never have imagined. Particle accelerators, nuclear reactors, quantum chemistry, semiconductor engineering, and quantum information science all rely on the principles that trace back to his work. Modern electronics operate because electrons in materials behave according to quantum mechanical rules. The development of the transistor, one of the most important technological innovations in history, depended entirely on understanding the quantum behavior of electrons in solids. Without the transistor, computers as we know them would not exist. Every smartphone, every communication satellite, every digital circuit is ultimately an application of quantum theory. In addition to electronics, quantum theory underlies many medical technologies. Magnetic resonance imaging, for example, depends on the quantum properties of atomic nuclei in magnetic fields. The study of molecules and chemical reactions also depends heavily on quantum mechanics. Chemistry as a discipline was transformed by quantum theory, since the behavior of atoms and bonds is fundamentally quantum mechanical. Thus, Planck's influence extends far beyond physics into every science that deals with the structure of matter. Today, new fields such as quantum computing and quantum cryptography aim to harness quantum effects in ways that classical systems cannot replicate. Quantum computers use superposition and entanglement to perform calculations that would take classical computers exponentially longer. These technologies are still in experimental stages, but they represent a future shaped directly by Planck's original insight. His discovery did not merely solve an isolated scientific puzzle. It opened a path toward entire technological worlds that continue to unfold. Reflecting on Planck's role in shaping modern physics also highlights the nature of scientific revolution. Revolutions in science do not always come from dramatic declarations or the rejection of old ideas. Sometimes they arise from attempts to solve specific, practical problems. Planck did not set out to overthrow classical physics. He sought to solve the Blackbody radiation problem, and in doing so uncovered a principle that required a new conception of reality. His willingness to follow evidence, even when it contradicted his expectations, exemplifies the essence of scientific inquiry. Progress comes not from holding onto theories, but from adjusting them when nature demands it. Planck's work also illustrates how simple mathematical expressions can carry profound conceptual meaning. Planck's equation, E equals h nu, is deceptively simple. It relates energy to frequency through a constant. Yet behind this simplicity lies a fundamental statement about the nature of the universe. Energy is quantized. Many of the most significant scientific discoveries share this characteristic. They reveal deep insights about the world through concise expressions. The power of Planck's constant lies not in complexity, but in its universal applicability. The influence of Planck's role on modern physics is therefore multidimensional. It altered the direction of scientific thought, provided the foundation for new theories, influenced generations of scientists, shaped technological development, and contributed to philosophical discussions about reality and knowledge. His work stands at the boundary between classical and modern physics, marking the point where one world, ended and another began. The modern era of physics is defined by two great pillars, quantum mechanics and relativity. Planck's discovery initiated the first, and his support for Einstein helped the second gain acceptance. The unity of these two frameworks continues to guide research in fundamental physics today, including attempts to develop quantum gravity and unify the forces of nature. Even now, more than a century after Planck's discovery, physicists are still exploring the consequences of quantum theory. Thus, Max Planck shaped modern physics not only by creating quantum theory, but by demonstrating how science proceeds when old ideas no longer match observed reality. His work stands as a testament to intellectual courage, persistence, and the willingness to question foundational beliefs. His legacy continues to influence scientific research, technological progress, and human understanding of the physical universe. The discovery of energy quanta began with a problem that appeared simple but defied all existing physical theory. Scientists studying heat radiation in the late 19th century were attempting to understand how objects emit and absorb energy. When materials are heated, they give off light in patterns that change with temperature. This emission has a specific intensity at different wavelengths. Physicists wanted an equation that would describe this spectrum accurately. They measured it carefully and found that the curve rose from lower intensities at long wavelengths to a peak, and then dropped off again at shorter wavelengths. Classical physics, however, could not create a theory that matched these measurements consistently. The existing laws predicted absurd results at high frequencies, implying that objects should emit unlimited energy in the ultraviolet range. This theoretical failure became known as the ultraviolet catastrophe. In reality, such endless energy emission does not occur. Yet, the best physics of the time insisted it should. This contradiction signaled a gap in scientific understanding that could not be ignored. Max Planck, a physicist trained in thermodynamics, approached this problem with great care. He sought a law that would fit experimental data without destroying the structure of classical physics. He believed deeply in continuity and determinism, the core assumptions of existing theory. When studying blackbody radiation, he tried to preserve these beliefs. He initially used traditional thermodynamic equations and classical statistical mechanics, but every attempt failed. The data refused to agree with theory. Planck realized that something fundamental must be reconsidered. Instead of trying to force classical assumptions to work, he took an unconventional step. He looked at the energy of oscillators, tiny idealized systems representing how atoms might vibrate and emit radiation, and proposed that these oscillators did not exchange energy in infinitely divisible amounts. Instead, they exchanged energy in fixed packets proportional to the frequency of radiation produced. This was the decisive moment. Planck introduced the idea that energy is quantized. Energy could only exist in integer multiples of a basic unit. E equals h nu, where E is energy, nu is frequency, and h is a constant that would come to bear his name. The constant h had to be extremely small in everyday units, which explained why quantization had never been observed at ordinary scales. At the atomic level, however, the effects were enormous. This single equation allowed Planck to match the blackbody radiation curve to experimental results perfectly. The severe theoretical crisis that had resisted solution for decades was suddenly resolved. Planck's law described nature precisely where classical physics failed. Yet the meaning of this law was revolutionary. It implied that the energy of systems is not smooth or continuous. There are smallest possible increments, indivisible and exact. This contradicted one of the most deeply held assumptions in physics. Classical theory assumed that any physical quantity could be divided indefinitely. Just as a mathematical line has no smallest segment, so energy was believed to have no smallest unit. Planck's discovery overturned this belief. Nature, at its foundation, does not behave like the continuous world visible to human perception. Instead, it behaves in discrete steps. The idea of energy quanta revealed that the microscopic world operates under rules very different from the macroscopic world. It showed that reality could be fragmented at fundamental scales, even though the larger world appears smooth. Initially, Planck did not interpret his own discovery in dramatic terms. He treated it as a mathematical adjustment necessary to make sense of thermodynamic behavior. He did not claim that physical systems truly possessed only discrete energies. He suspected that someone would eventually reinterpret his equation within classical terms. However, experiments and theoretical developments soon made it clear that the quantum was not merely a computational convenience. It reflected an inherent feature of nature. Other physicists began examining phenomena in light of Planck's idea. One of the earliest was Albert Einstein. Einstein realized that Planck's discovery could explain the photoelectric effect, in which light striking metal surfaces releases electrons. Classical wave theory predicted that increasing the intensity of light would increase energy transferred to electrons, regardless of frequency. Experiments contradicted this. Only light above a certain frequency caused electrons to be ejected, no matter how bright the light was. This behavior made no sense unless light itself consisted of quanta, photons carrying energy in discrete packets proportional to frequency. Einstein's work supported Planck's interpretation, but extended its significance beyond oscillators to the nature of light itself. This marked a profound shift. Light was no longer only a wave, but also a particle-like entity. As more evidence accumulated, the concept of energy quanta gained strength. Atomic spectra, which show that atoms emit and absorb light only at specific frequencies, could only be understood if atoms themselves possessed quantized energy levels. Classical models had predicted that electrons orbiting a nucleus should radiate continuously and collapse inward. Yet atoms were stable. The idea of quantized states explained this stability. Electrons could only occupy specific allowed energy levels and could not fall below a minimum energy state. When electrons moved between levels, they emitted or absorbed quanta of light with energies exactly matching Planck's formula. This discovery linked atomic structure directly to Planck's constant. The quantum became the key to unlocking the architecture of matter. The discovery of energy quanta also revealed a new understanding of measurement. In classical systems, we assume that we can observe properties of a system with unlimited precision. In quantum systems, however, the act of observation itself affects the state of what is being measured. When energy exists only in discrete states, transitions between them do not occur gradually. They happen as sudden changes. The concept of continuity, widely taken for granted in classical thought, loses meaning at microscopic scales. Events do not unfold through smooth intermediate stages. They leap from one outcome to another. This redefined the nature of causation. Instead of every outcome being determined precisely by previous conditions, quantum behavior involves probabilities. The discovery of quanta, therefore, challenged not only physical equations, but also the underlying logic used to interpret physical processes. Planck himself remained reserved in drawing philosophical implications. He recognized the significance of his constant, but did not embrace the broader conceptual upheaval that followed. He viewed the quantum as a necessary adjustment rather than a fundamental revolution. However, scientific developments after his initial discovery proved otherwise. The quantum was not an obscure correction. It was the foundation of a new field. The behavior of light, electrons, atoms, and molecules all followed patterns that could not be explained without quantization. The forces binding matter, the spectra of stars, chemical reactions, and even the properties of solids all depended on energy quanta. As physicists explored these implications, the nature of the quantum revealed a universe governed by mathematical structures that had no counterpart in classical physics. For instance, the wave-like behavior of particles later demonstrated in experiments showing electron diffraction could only be understood if particles possessed dual identities. They were not purely localized or purely extended. Instead, they were described by wave functions that predicted the probabilities of physical outcomes. The quantum, therefore, provided a new kind of description of reality. Rather than describing physical objects in fixed, deterministic terms, quantum theory describes systems as distributions of probability, with energy levels and transitions governed by discrete quanta. Planck's discovery revealed that certainty is not fundamental at microscopic scales. It is an emergent property that appears only when the effects of quantization average out across large numbers of particles. The discovery of energy quanta also demonstrated the profound power of theoretical reasoning supported by empirical evidence. Planck did not observe quanta directly. None of the equipment of his time could detect single photons or electrons changing quantized levels. Instead, Planck inferred the existence of quanta through mathematical necessity. The theoretical curve fit the data only when energy was quantized. Later experimental verification confirmed his conclusion. This sequence, mathematical insight leading physical discovery, became a hallmark of 20th century physics. The idea of energy quanta provided a framework that allowed physicists to explore realms that could not be observed directly. It enabled the construction of new theories of matter and radiation that replaced older models. The quantum was therefore not just a discovery, but a gateway to vast new domains of scientific inquiry. Planck's discovery also demonstrated that progress in science sometimes requires abandoning assumptions so deeply rooted that they seem undeniable. The idea of continuity was assumed rather than proven. Planck's work showed that what appears intuitively natural may not describe nature accurately at all. This lesson applies not only to physics, but to scientific methodology as a whole. To achieve progress, scientists must be prepared to question foundational principles when evidence demands it. Planck set the example by following logic rather than expectation. His discovery illustrates how the greatest advances occur when theory aligns with observation rather than tradition. The concept of energy quanta teaches that nature is not bound by human intuition, but by underlying laws that must be revealed through careful analysis. Thus, the discovery of energy quanta represents one of the most profound moments in the history of science. It replaced a continuous universe with one composed of discrete units. It changed the understanding of light, heat, matter, and motion. It created the foundation on which quantum mechanics was built. It influenced the development of modern technology, from semiconductors to lasers to quantum computation. It reshaped philosophical perspectives on certainty, causation, and the nature of physical reality. Planck's introduction of quantized energy marked the beginning of the modern scientific era. It stands as a testament to the power of theoretical reasoning and the willingness to challenge long-held assumptions when confronted with evidence that demands change. The full meaning of the discovery of energy quanta unfolded gradually as scientists tested Planck's assumptions across different branches of physics. One of the earliest and most significant confirmations came from studies of atomic structure. When heated gases glowed and emitted light, they did not produce a continuous spectrum of colors, but instead produced sharp, distinct spectral lines. These lines were signatures of specific energies emitted and absorbed by atoms. Classical theory attempted to explain this behavior, but failed. If electrons were orbiting the nucleus like planets around the Sun, classical electromagnetic theory predicted that they would radiate energy constantly, spiral inward, and collapse into the nucleus. Such collapse did not happen. Atoms remained stable. The existence of sharp emission lines indicated that electrons could occupy only certain stable states. The discovery of energy quanta provided a direct explanation. Electrons moved only between allowed energy levels and emitted or absorbed energy in discrete units as they made transitions. The frequencies of the emitted light matched Planck's formula. This established a direct connection between atomic structure and energy quantization. The idea that electrons do not radiate energy continuously resolved multiple inconsistencies in classical theory. Before the discovery of quanta, physicists were forced to hypothesize invisible mechanisms to stabilize atoms. These mechanisms lacked mathematical support. Planck's discovery provided the missing foundation. It not only explained stability, but also made quantitative predictions. The matching of spectral data from different gases revealed a universal behavior shared by all atoms, signaling that the quantum was not a special case, but a general law governing matter and light. At the fundamental level, this was the clearest demonstration that classical physics was not universally applicable. Instead, its validity was limited to large-scale systems in which the discrete nature of energy becomes negligible due to large numbers of particles averaging out quantized effects. Another major development that solidified the role of energy quanta was the work of Niels Bohr. Bohr proposed a model of the hydrogen atom based directly on the assumption that electrons occupied discrete energy levels. This model reproduced the exact spectral lines observed in experiments. The fit was precise and unforced. It showed that the quantum concept was aligned with nature rather than being a mathematical trick. Although Bohr's model would later be replaced by more sophisticated quantum mechanical models, it demonstrated that quantization could produce accurate predictions where classical physics could not. This was a turning point. The quantum was no longer an isolated solution to a radiation problem. It was a general principle underlying the structure of matter. Following Bohr, Werner Heisenberg and Erwin Schrödinger developed complete quantum mechanical theories that formalized how quanta governed physical systems. Heisenberg's matrix mechanics and Schrödinger's wave mechanics were mathematically different, but converged to the same conclusions. The consistency between independent formulations provided strong support for the reality of quantized systems. Schrödinger's wave mechanics introduced the idea of the wave function, describing states of particles not as fixed positions, but as probability distributions. This model explained why discrete energy levels exist. Waves in a confined region can only form patterns of specific shapes. Each pattern corresponds to a quantized level. The discovery of energy quanta therefore revealed that particles behave like standing waves in constrained environments. This clarified the nature of atomic structure in mathematical terms. As quantum mechanics developed, Planck's constant appeared repeatedly as the one parameter linking energy, frequency, and the action of physical systems. Its presence across equations indicated that it was not simply a scaling factor, but a fundamental measure of nature's smallest interactions. The discovery that reality operates in quanta led to a new understanding of measurement. Heisenberg identified that certain physical quantities, such as position and momentum, could not be simultaneously known with unlimited precision. The uncertainty principle arises from the quantized nature of energy and the wave-like properties of particles. If a particle behaves like a wave, and waves have spread-out distributions, then exact location and exact momentum cannot both be defined. This principle did not reflect limitations of experimental tools, but inherent features of physical systems. The discovery of energy quanta thus changed the meaning of scientific observation. Measurement was no longer a passive act revealing pre-existing properties, but an interaction that influenced system behavior. The discovery of quanta also reshaped the understanding of radiation and matter interaction. Classical theory viewed energy transfer between matter and radiation as smooth and continuous. The quantum perspective revealed that such interactions occur in discrete steps. For example, when electrons absorb photons, they do not gradually gain energy. They either gain the full quantum required to reach the next energy level, or they do not absorb energy at all. This rule explains why atoms interact selectively with light of specific frequencies. Energy exchange is quantized, and this selectivity forms the basis of countless physical processes. The laser, for example, is a direct application of controlled stimulated emission, in which electrons drop from higher to lower energy states and release photons of identical frequency and phase. Without the discovery of energy quanta, lasers would not exist. The discovery of quanta also made it possible to understand chemical bonding. Classical models could not explain why atoms formed stable molecules or why different elements reacted in specific ways. Quantum mechanics revealed that bonding arises from electron-wave functions overlapping and forming stable distributions that minimize energy. These distributions depend on the quantized energy states of electrons. Modern chemistry is grounded entirely in quantum theory. The periodic table, bond types, reaction rates, molecular structures, and material properties all follow from the discrete nature of energy. The discovery of quanta transformed chemistry from a descriptive science to a predictive one. It allowed scientists to calculate molecular properties theoretically, leading to the design of materials, pharmaceuticals, and industrial compounds. The influence of the discovery of quanta extended into condensed matter physics, where the properties of solids and metals were explained for the first time. Classical theory could not describe why some materials conduct electricity and others do not. Quantum mechanics showed that electrons in solids occupy quantized energy bands. Conductors allow electrons to move freely because they have partially filled bands. Insulators have full bands separated by large gaps of forbidden energy. Semiconductors have small gaps that allow controlled electron flow. This understanding led to the invention of the transistor, the fundamental component of modern electronics. Without the concept of quantized energy bands, the transistor would be impossible. The digital revolution is a direct consequence of Planck's discovery. The discovery of quanta also had implications for nuclear physics. The forces binding protons and neutrons in atomic nuclei could not be explained using classical electric and mechanical forces. Quantum mechanics provided the framework for understanding nuclear stability and decay. Nuclear reactions release large amounts of energy because they involve transitions between quantized states in the nucleus. The development of nuclear energy, both for power generation and for weapons, depended on the quantum understanding of nuclear binding. Although Planck could not have predicted these outcomes, they emerged inevitably from the principles he introduced. Another major influence was the emergence of quantum field theory, which unites quantum mechanics with special relativity. Quantum field theory describes particles not as permanent objects, but as excitations in underlying fields. Every type of particle corresponds to a quantized field. The discovery of energy quanta made this interpretation possible. Each particle becomes a unit of quantized energy in its field. This theory underlies the standard model of particle physics, which describes electromagnetic, weak, and strong nuclear interactions. These advances demonstrate that the discovery of quanta extended far beyond the original context of thermal radiation. It reshaped the understanding of all forces and particles. The philosophical implications of the discovery are substantial. Classical physics presented a world governed by certainty, continuity, and determinism. The discovery of quanta introduced discontinuity, discreteness, and probability. The structure of reality became statistical rather than absolute. This did not mean that physical laws ceased to exist. Instead, It meant that laws operate differently at different scales. Classical behavior emerges only when quantized effects average out across large numbers of interacting particles. At the microscopic level, energy quanta define the limits of physical possibility. At the macroscopic level, classical behavior arises as an approximation. The discovery of quanta therefore unified the two views. Classical physics was not wrong but incomplete, valid only in certain domains. The discovery of energy quanta also demonstrates a broader principle about scientific knowledge. Scientific theories are not final truths. They are models that describe nature to the extent that current evidence allows. When new evidence emerges, theories may need to be revised or replaced. Planck's work exemplifies this process. Classical theory worked well for many systems, but failed in explaining blackbody radiation. Planck observed the discrepancy and adjusted theory to match reality. The result was the discovery of quanta. This approach is the foundation of scientific progress. It requires openness, precision, and willingness to reconsider assumptions. The discovery of energy quanta continues to influence new fields of research today. Quantum computing, for example, relies on qubits that exist in superpositions of states. This ability to occupy multiple states simultaneously is a direct consequence of quantum principles. Quantum communication uses entanglement to transmit information securely. Quantum sensing exploits the sensitivity of quantized systems to detect extremely small changes in physical quantities. These fields are still developing, yet they already demonstrate that the discovery of quanta remains central to technological innovation. The discovery of energy quanta, therefore, represents a moment when science crossed a boundary into a new conceptual framework. It changed the understanding of energy, matter, and light. It redefined the meaning of measurement and prediction. It altered the structure of chemistry and solid-state physics. It led to the development of modern electronics, nuclear physics, quantum field theory, and emerging quantum technologies. Planck's introduction of quantization was not merely a correction to existing theory. It was the foundation of a new scientific world view. It stands as one of the most significant achievements in the history of physics, shaping not only scientific research, but also the technological structure of modern society. The discovery of energy quanta fundamentally challenged the assumptions on which classical physics had been built for centuries. Classical physics, developed from the work of figures such as Isaac Newton and James Clerk Maxwell, was grounded in the belief that nature is continuous, deterministic, and mathematically predictable. According to this world view, all physical processes could be described with smooth and unbroken quantities. Motion, energy, and force were assumed to vary continuously, and with enough information, the past and future states of any system could be known exactly. This framework worked well for describing the behavior of planets, falling objects, mechanical systems, and electromagnetic waves. For a long time, it appeared to provide a complete explanation of the natural world. However, the emergence of phenomena that classical physics could not explain revealed limitations in its assumptions. The ultraviolet catastrophe, atomic spectral lines, and the stability of atoms were only a few examples. When physicists attempted to explain blackbody radiation, classical equations predicted infinite energy emission at high frequencies, which was physically impossible. This failure suggested that the classical assumption of continuous energy was incorrect. Planck's introduction of quantized energy directly contradicted classical principles. By proposing that energy could only be emitted or absorbed in fixed amounts, Planck introduced discontinuity into the physical world. Instead of energy flowing smoothly, it jumped in discrete steps. This was a radical departure from the continuous mathematics of classical theory. The challenge to classical physics became even clearer as scientists applied quantization to the structure of the atom. Classical theory predicted that electrons orbiting a nucleus should radiate energy continuously and lose speed, eventually collapsing into the nucleus. But atoms are stable. The only explanation was that electrons did not radiate energy continuously. They could only change energy when moving between distinct allowed states. This showed that classical mechanics could not describe atomic behavior. The stability of matter itself depended on quantized energy levels, which classical physics had never anticipated. This discovery demonstrated that classical assumptions were valid only at large scales, where the effects of quantization average out. At microscopic scales, nature obeys different rules. Another classical assumption challenged by quantum theory was determinism. Classical physics assumed that the future behavior of a system could be predicted exactly if its present state was known. The discovery of energy quanta gradually led to the realization that such exact prediction is not possible at atomic and subatomic scales. Werner Heisenberg's uncertainty principle showed that certain pairs of physical quantities, such as position and momentum, cannot both be known with complete precision. This was not due to limitations of measurement instruments, but to the fundamental nature of quantum systems. The behavior of particles is described by probability distributions rather than fixed values. The outcome of a quantum event cannot be predicted exactly, only the likelihood of different results. This represented a profound shift in understanding. Classical physics viewed uncertainty as resulting from lack of information. Quantum physics showed that uncertainty is inherent in the structure of reality. Classical physics also assumed that light was purely a wave phenomenon, based on Maxwell's electromagnetic theory. The quantum explanation of the photoelectric effect demonstrated that light also behaved as a particle. Einstein's interpretation of Planck's quantum of energy as a particle of light challenged the classical wave theory. Light could no longer be understood within the classical framework alone. It had a dual nature, behaving as both wave and particle depending on the experiment. This duality contradicted the classical expectation that objects should have a single well-defined nature. The quantum world, therefore, required new concepts that could accommodate multiple forms of behavior simultaneously. The discovery of quanta also challenged classical assumptions about causality. In classical physics, every effect had a definite cause, and interactions followed continuous paths. In quantum systems, interactions are quantized, and transitions between states occur without intermediate stages. An electron does not gradually move from one orbital to another. It disappears from one state and appears in another, releasing or absorbing a quantum of energy. There is no classical transition path. The lack of intermediate states directly contradicts classical intuition about how physical processes unfold. Nature operates in discrete jumps, not smooth evolutions, at the smallest scales. These challenges did not mean that classical physics was invalid. Rather, they showed that classical physics is an approximation that applies only to large systems where quantized effects are negligible. The world that humans interact with on a daily basis consists of enormous numbers of particles, and the average behavior of these particles smooths out quantized effects. Classical physics remains extremely useful for describing macroscopic systems such as planetary motion, bridges, engines, and electrical circuits. However, The discovery of quanta revealed that this usefulness does not imply universal accuracy. The laws governing the microscopic world do not mirror the laws observed at human scales. Instead, classical laws emerge statistically from quantum laws. The challenge to classical physics assumptions also had philosophical implications. Classical physics suggested a universe that was fully knowable, predictable, and governed by fixed laws that operated in a straightforward manner. Quantum physics revealed a universe with fundamental indeterminacy, discontinuity, and duality. Reality became something that could not be fully described in purely visual or mechanical terms. Mathematical abstractions replaced intuitive imagery. The idea of a world that behaves according to deterministic rules had to be replaced with a world in which probability and uncertainty are intrinsic features of physical existence. Therefore, the discovery of energy quanta was not simply the introduction of a new formula or constant. It was a deep challenge to the foundational assumptions of classical physics. It forced scientists to reconsider the nature of matter, energy, prediction, and measurement. It showed that the universe is structured in layers, with classical behavior emerging from underlying quantum rules. This transformation marked the beginning of modern physics and reshaped the understanding of the physical world. The classical world did not disappear, but it became recognized as a limited case within a broader quantum reality. The discovery of quanta revealed that the universe is more complex than previously believed, and that true understanding requires models that reflect the discrete and probabilistic nature of fundamental physical processes. Planck's constant is one of the most important and fundamental values in modern physics. It represents the scale at which quantum effects become noticeable and marks the boundary between the classical world of everyday experience and the quantum world of atoms and subatomic particles. Max Planck introduced this constant while searching for a formula that could describe the radiation emitted by heated bodies. His discovery was not meant to revolutionize physics at the time, but it eventually became the foundation upon which the entire framework of quantum theory was built. Planck's constant is important because it defines the size of the discrete packets, or quanta, in which energy is exchanged. It shows that energy is not continuous, but exists in fixed amounts depending on frequency. This idea was entirely new and challenged all previous assumptions about the nature of energy. The value of Planck's constant is extremely small, which explains why quantum effects are not noticeable in daily life. Everyday objects consist of enormous numbers of particles interacting in ways that smooth out any discrete behavior. Therefore, classical physics appears to work perfectly well for large-scale systems. However, when we examine the world at atomic scales, the smallness of Planck's constant becomes crucial. It tells us that the transitions of atoms, electrons, light, and other particles occur in steps so tiny that they cannot be detected in macroscopic interactions, but are essential in understanding microscopic behavior. This constant therefore acts as a gateway to the quantum world, helping scientists identify when classical descriptions fail and quantum rules must take over. Planck's constant also plays a key role in describing the dual nature of light. When Einstein used Planck's idea to explain the photoelectric effect, he argued that light was made of particles called photons, each carrying energy equal to Planck's constant multiplied by its frequency. This interpretation showed that light could behave both as a wave and as a particle. The constant formed a direct mathematical bridge between frequency, which is a wave property, and energy, which is a particle property. Without Planck's constant, such a connection could not exist. This duality lies at the heart of quantum mechanics and demonstrates how deeply Planck's constant is embedded in the core structure of physical theory. Planck's constant is also involved in the concept of quantized angular momentum. Electrons orbit the nucleus of an atom not in continuous paths like planets around the Sun, but in fixed energy levels. Each allowed orbit corresponds to an angular momentum value that is an integer multiple of Planck's constant divided by 2 pi. This means that electrons cannot exist at arbitrary locations around the nucleus. They can only occupy specific levels. This is one of the key ideas that led to the development of atomic theory and the Bohr model, which in turn laid the foundation for quantum mechanics. Planck's constant determined the spacing between these levels and explained spectral lines in atomic emission. When atoms absorb or emit energy, they do so by absorbing or releasing a quantum of energy whose magnitude depends on Planck's constant. Another essential role of Planck's constant arises in the Heisenberg uncertainty principle. This principle states that certain pairs of properties, such as position and momentum, cannot be simultaneously known to perfect accuracy. The product of the uncertainties in these measurements is proportional to Planck's constant. Therefore, the constant represents the fundamental limit on how precisely we can measure and predict quantum behavior. It shows that uncertainty is not a matter of experimental limitations, but is built into the structure of reality. The existence of this limit marks a major departure from the determinism of classical physics. The universe is not a predictable machine operating with mechanical precision, but a system in which probabilities govern behavior at the smallest scales. Planck's constant also directly affects the structure of modern technology. Devices such as lasers, transistors, semiconductors, LEDs, and atomic clocks depend on quantum principles that are rooted in Planck's constant. For example, semiconductor behavior depends on electrons moving between quantized energy levels in materials. Lasers work because atoms are stimulated to emit photons of identical energy, which is determined by Planck's equation. Atomic clocks, the basis of global positioning and telecommunications timing, rely on extremely precise measurements of energy transitions between specific atomic states, again determined by Planck's constant. Therefore, this constant is not just a theoretical value, but an essential component of the technological infrastructure of the modern world. Planck's constant also plays a role in defining new standards of measurement. In 2019, the kilogram, which is the fundamental unit of mass in the International System of Units, was redefined using Planck's constant rather than a physical object. This shows how deeply embedded the constant has become in precision science. Instead of depending on an external artifact, scientists now use fixed, universal physical constants to define measurement units. This ensures accuracy and stability that do not change over time. Planck's constant therefore contributes to the reliability and consistency of scientific research and global measurement systems. Beyond its scientific and technological importance, Planck's constant has philosophical implications. It represents the idea that nature at its core is not continuous and smooth, but granular and discrete. This contradicts centuries of classical thought, which viewed the universe as infinitely divisible and reversible in time. The existence of a smallest meaningful action, which is what Planck's constant represents, indicates that there are limits to resolution, observation, and predictability. It suggests that the laws of nature are probabilistic, and that the universe has a deeper and more intricate structure than classical physics ever imagined. In conclusion, Planck's constant is a fundamental value that defines the scale at which quantum effects dominate. It introduced the idea of quantization, making possible the development of quantum mechanics. It connects wave and particle behavior, determines the structure of atoms, governs uncertainty, shapes modern technology, and serves as a standard for measurement. Its discovery changed the course of physics and altered humanity's understanding of nature at the most fundamental level. The constant stands as both a symbol and a tool of the quantum revolution initiated by Max Planck, a revolution that continues to influence science and technology today. Planck's introduction of energy, quanta, had a direct and powerful influence on Albert Einstein, who expanded the idea far beyond what Planck initially intended. Although Planck used quantization mainly as a mathematical tool to solve the Blackbody radiation problem, Einstein recognized that the quantum concept represented a real physical property of nature. This insight marked a turning point, transforming quantum theory from a temporary adjustment to classical physics into a revolutionary framework that reshaped science. The relationship between Planck's work and Einstein's interpretation demonstrates how a single idea, once extended and applied, can alter the course of scientific history. Planck wisely opened the door, and Einstein walked through it with boldness that even Planck initially hesitated to adopt. Einstein's first major contribution to quantum theory was his explanation of the photoelectric effect in 1905. Experimental results showed that when light shines on a metal surface, electrons are ejected from the metal. Classical wave theory predicted that increasing the intensity of the light should increase the energy of the ejected electrons. However, experiments demonstrated something different. Increasing the intensity increased the number of electrons released, not their energy. The energy of the electrons depended only on the frequency of the light, not its brightness. Classical physics could not account for this. Einstein used Planck's quantum hypothesis to argue that light itself must consist of individual packets of energy, later called photons. The energy of each photon is equal to Planck's constant multiplied by the frequency of the light. This explanation matched experimental behavior perfectly. Einstein's interpretation was revolutionary because it asserted that quantization was not just a mathematical convenience, but a fundamental property of light. Planck had avoided claiming such a physical interpretation, as he believed strongly in the continuity of natural processes. However, Einstein's boldness gave quantum theory physical meaning. By extending the idea beyond radiation emission to the nature of light itself, Einstein set the stage for quantum mechanics to develop as a broader theory. Planck initially remained cautious and did not immediately accept the particle nature of light, demonstrating that scientific revolutions sometimes require multiple thinkers working in succession, each pushing the idea further than the previous one. The influence of Planck on Einstein did not end with the photoelectric effect. Einstein also used the quantum concept to explain heat capacity in solids. Classical physics predicted that heat capacity should be constant, but experimental data showed that heat capacity decreases at low temperatures. Einstein applied Planck's quantization to vibrations of atoms in a solid, suggesting that these vibrations also occur in discrete steps rather than continuously. This idea showed that quantization is not limited to radiation, but applies to the behavior of matter as well. This strengthened the foundation for quantum theory and demonstrated its broad applicability. Planck, in turn, recognized Einstein's contributions and supported him scientifically, even when other scientists resisted Einstein's ideas. When Einstein faced opposition from established physicists who rejected the quantum interpretation, Planck defended the importance of his work. Planck's support was essential in helping Einstein gain acceptance, encouraging the scientific community to consider quantum theory seriously. Their relationship demonstrated mutual respect and intellectual collaboration, even though they often disagreed on interpretation. Planck valued caution and philosophical stability, while Einstein valued conceptual boldness and willingness to challenge assumptions. This balance of perspectives helped quantum theory advance without losing scientific rigor. As quantum theory progressed, other scientists expanded on Planck's and Einstein's work. Niels Bohr used Planck's constant to construct the first model of the atom, showing that electrons occupy discrete energy levels. Werner Heisenberg and Erwin Schrödinger later developed mathematical frameworks that described the behavior of quantum systems in ways that did not depend on classical analogies. All of these developments trace back to the idea of quantized energy, the concept Planck introduced. Without Planck's constant, the mathematics of quantum mechanics would not exist, and without Einstein's expansion of the idea, the physical interpretation of quantum theory might have remained undecided. Einstein eventually became critical of some aspects of quantum mechanics, especially the idea that physical events are governed by probability rather than certainty. He famously stated that God does not play dice with the universe, expressing discomfort with the role of randomness introduced by quantum theory. This disagreement did not diminish the role he played in shaping the theory's foundations. Rather, it highlighted how revolutionary the consequences of Planck's original idea were. Even those who expanded quantum theory did not always agree with where it led. Planck himself maintained cautious skepticism, while Einstein challenged the meaning of quantum uncertainty, and scientists like Bohr defended probability as an essential feature of nature. The diversity of views reflects the depth and complexity of quantum theory's development. Planck's influence on Einstein and on quantum mechanics demonstrates the continuity of scientific progress. Scientific revolutions rarely occur in isolated steps. Instead, ideas evolve and grow as new thinkers reinterpret them. Planck provided the first insight, Einstein recognized its deeper implications, and subsequent physicists built the mathematical and philosophical structure that became modern quantum mechanics. Without Planck's constant, the quantum world could not be measured or described. Without Einstein's interpretation, the quantum would not have gained physical meaning. Without the later theorists, the quantum framework would not have matured into a complete theory. The impact of this collaboration and progression is visible in modern technology and scientific understanding. Quantum mechanics forms the basis of nearly all advanced electronics, communications, computing systems, lasers, and medical imaging technologies. The ideas that began with Planck and were extended by Einstein now shape global infrastructure and scientific research. Their intellectual partnership is thus not merely a historical curiosity, but a foundation of the modern world. In summary, Planck's influence on Einstein and the development of quantum mechanics reveals the deep connections between theoretical insight and scientific progress. Planck introduced the idea of quantization. Einstein recognized its profound physical meaning, and together these ideas reshaped physics. Their interaction illustrates how scientific change occurs through the interplay of caution and daring, calculation and interpretation. The quantum theory that emerged from this dialogue continues to define modern science and technology, showing that the transformations sparked by Planck's constant reach far beyond the laboratory and into every aspect of contemporary life. The introduction of quantum theory by Max Planck triggered a profound shift not only in scientific understanding, but also in the philosophical interpretation of reality. Before quantum theory, the world, shaped by classical physics, presented the universe as a predictable, orderly system governed by fixed laws. According to this classical outlook, the world functioned like a finely crafted machine. If one knew the position and motion of every particle, one could calculate all future events with certainty. This belief in strict determinism shaped science, philosophy, and even cultural thought. Quantum theory disrupted this world, by revealing that the universe is not entirely predictable, continuous, or deterministic. Instead, it behaves in ways that involve probability, discontinuity, and uncertainty at its most fundamental levels. One of the most significant philosophical implications of quantum theory is the rejection of absolute certainty in physical processes. Planck's discovery showed that energy exists in discrete packets rather than continuous flows. This meant that the behavior of matter and radiation could not be described using smooth mathematical functions alone. Later developments, such as Heisenberg's uncertainty principle, revealed that certain physical quantities cannot be measured simultaneously with perfect accuracy. This uncertainty is not due to limitations of instruments, but is a fundamental property of nature. The realization that nature itself limits what can be known overturned the classical idea that complete knowledge is theoretically possible. It introduced a new understanding. At the smallest scales, the universe operates on probabilities rather than certainties. Quantum theory also challenged the classical belief that objects have fixed, definite properties independent of observation. In classical physics, an object has measurable characteristics regardless of whether someone observes it. Quantum mechanics, however, demonstrated that the state of a particle can exist in multiple possible forms until an observation or measurement is made. This phenomenon is often illustrated by the idea of superposition, in which a particle can occupy several states simultaneously. The act of measurement forces the system into one particular state. This raised deep philosophical questions about the relationship between observer and reality. It suggested that human observation is not a passive act, but an active participant in determining physical outcomes. The boundary between subject and object, which classical philosophy had treated as absolute, became unclear. Another important philosophical shift caused by quantum theory involves the concept of causality. Classical physics assumed that every event has a specific cause that can be traced through time. Quantum physics showed that events at the atomic level can occur without traditional causation. A particle may spontaneously change its state or position without any identifiable driving force. This randomness is not a result of hidden variables or unknown influences, but an intrinsic part of quantum behavior. Such randomness was deeply unsettling to scientists like Einstein, who believed that the universe must have underlying order and purpose. However, the acceptance of randomness became central in quantum mechanics, introducing a new model of causation based on probability distributions rather than fixed deterministic laws. Quantum theory also altered the understanding of identity and individuality in nature. In the classical world, objects are distinct from one another and can be labeled and tracked consistently. In quantum physics, particles such as electrons are fundamentally indistinguishable. They do not have individual identity in the way classical objects do. This indistinguishability affects how systems behave when particles interact or are exchanged. The behavior of systems is determined not by the identity of individual particles, but by collective statistical properties. This shift challenged philosophical notions of individuality and separateness, suggesting that at the deepest levels of nature, identity is fluid and relational. The quantum world view also influenced broader cultural and intellectual perspectives. In the early 20th century, classical determinism supported the idea that progress, science, and human reasoning would eventually uncover all truths. Quantum uncertainty introduced a recognition of limits, complexity, and ambiguity. This influenced fields outside physics, including philosophy, literature, art, and psychology. Intellectual movements began to embrace themes of uncertainty, paradox, and subjectivity. The idea that different outcomes may coexist until observed resonated with modern discussions about perception and reality. Quantum theory encouraged thinkers to question assumptions of absolute truth and consider multiple perspectives. At the same time, quantum theory did not imply that the universe is chaotic or meaningless. Instead, it revealed that order and pattern arise from probabilities rather than rigid certainty. The laws of quantum mechanics are precise and highly predictive at the statistical level. For example, the behavior of atoms in a gas or electrons in an electrical circuit can be predicted with great accuracy, even though the behavior of individual particles cannot. Quantum theory thus replaced the classical clockwork universe with a probabilistic universe governed by mathematical structure. It demonstrated that unpredictability and structure coexist, and that complexity can arise from simple underlying principles. This philosophical shift also affected the role of mathematics in science. Classical physics relied on mathematics to describe motion and forces in clear, continuous terms. Quantum mechanics required new forms of mathematics, such as wave functions, operators, and probability amplitudes. These mathematical structures describe a reality that cannot be visualized in everyday terms. This represented a shift from intuitive, picture-based understanding to abstract conceptual reasoning. Physics began to describe nature in ways that could not always be imagined visually. This required scientists to accept that human senses are limited and that deeper truths may be accessible only through mathematical abstraction. In conclusion, the rise of quantum theory marked a profound shift in both scientific and philosophical worldview. It replaced certainty with probability, continuity with discreteness, and determinism with a model that includes inherent uncertainty. It challenged assumptions about knowledge, identity, causality, and the relationship between observer and reality. It reshaped not only the field of physics, but also broader intellectual thought. Max Planck's discovery of energy, quanta, triggered a transformation in how humanity perceives the universe and its own ability to understand it. The world view that emerged from quantum theory is more complex, more nuanced, and more reflective of the depth and subtlety of the natural world. Max Planck's contribution to physics did not end with his introduction of quantum theory. His work laid the groundwork for an entirely new understanding of the physical universe and influenced generations of scientists who followed. To truly appreciate Planck's legacy, it is important to explore not only the scientific breakthroughs he achieved, but also how his ideas reshaped the philosophical approach to physics, inspired future discoveries, and created a lasting imprint on technology, education, and scientific thought. Planck's introduction of the quantum concept in 1900 challenged the established understanding of energy, matter, and radiation. Before Planck, classical physics, which included the laws of thermodynamics, Newtonian mechanics, and Maxwell's electromagnetic theory, assumed that energy could vary continuously. Planck's revolutionary idea that energy is quantized and exists in discrete units called quanta, opened the door to modern quantum mechanics. This insight not only resolved the long-standing problem of blackbody radiation, known as the ultraviolet catastrophe, but also forced physicists to reconsider the fundamental principles governing the behavior of nature at microscopic scales. His work demonstrated that classical physics could not fully describe atomic and subatomic phenomena, marking a pivotal turning point in science. Planck's influence extended far beyond his own research. He became a mentor and intellectual beacon for a generation of physicists who would go on to develop quantum mechanics in its full form. Figures such as Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger drew upon Planck's insights to formulate theories that would redefine physics. For instance, Einstein's explanation of the photoelectric effect relied directly on Planck's concept of energy quanta, earning him the Nobel Prize in 1921. Bohr's model of the atom, which introduced quantized electron orbits, also traced its origins to Planck's foundational ideas. In this way, Planck served as a bridge between classical physics and the revolutionary world of quantum mechanics, influencing both the theoretical and practical directions of science in the 20th century. Beyond the direct scientific impact, Planck's work had profound philosophical implications. The quantization of energy challenged the deterministic world view that classical mechanics had promoted for centuries. Instead of a universe entirely governed by continuous laws, Planck introduced a framework in which uncertainty and probability played a central role. This philosophical shift encouraged scientists to approach natural phenomena with a mindset that embraced complexity, non-intuition, and statistical reasoning. Planck himself was deeply reflective about the broader implications of his work, emphasizing that scientific discovery often involves incremental insights, persistence, and humility in the face of nature's intricacy. Planck also had a significant influence on scientific institutions and education. He was actively involved in the German Physical Society and various academic bodies, helping to shape the structure and culture of scientific research in Germany. By fostering a rigorous and collaborative scientific environment, Planck ensured that Germany became a hub for pioneering research in quantum physics, particularly during the early decades of the 20th century. His insistence on precision, mathematical rigor, and adherence to experimental evidence became a model for both students and colleagues. Even as political turmoil and societal upheavals affected Germany, Planck remained committed to the principles of academic freedom and scientific integrity, further cementing his role as a leader in the scientific community. Technologically, the implications of Planck's work continue to resonate. Quantum theory has paved the way for countless innovations, from semiconductors and lasers to modern computing and telecommunications. Planck's ideas about discrete energy levels underlie the functioning of quantum devices, and his legacy is visible in emerging fields like quantum computing, quantum cryptography, and nanotechnology. In many ways, the tools and conveniences of the modern technological world are rooted in the theoretical groundwork that Planck laid more than a century ago. Max Planck's personal qualities also contributed to his enduring legacy. He was known for his dedication, patience, and careful reasoning. Unlike some of his contemporaries, he pursued scientific truth with caution and depth rather than seeking immediate fame. He faced criticism and skepticism when proposing his quantum hypothesis, but remained steadfast, demonstrating the importance of perseverance in scientific inquiry. His moral and intellectual integrity, combined with his humility, inspired others to pursue rigorous and thoughtful research rather than chasing accolades. Even after his death in 1947, Planck's influence persists in both the scientific and cultural understanding of physics. The Max Planck Society, founded in his honor, continues to be one of the leading research institutions globally, conducting cutting-edge research across physics, chemistry, biology, and beyond. This institutional legacy ensures that Planck's name and ideals are continuously associated with innovation, excellence, and the pursuit of fundamental knowledge. In summary, Max Planck's legacy is multifaceted and enduring. His discovery of energy quantization revolutionized physics, setting the stage for quantum mechanics and reshaping our understanding of the universe. Beyond his scientific contributions, he influenced generations of physicists, redefined philosophical approaches to science, fostered academic excellence, and inspired technological innovations that continue to impact our daily lives. Planck exemplifies the profound influence a single thinker can have when curiosity, insight, and perseverance converge. His work remains a testament to the power of human intellect and the ongoing quest to uncover the fundamental truths of nature, making him rightfully remembered as the father of quantum theory.